have applications in every field of human endeavor. They combine precision and computational power with pure logic to solve problems and reduce error in operation. Already, robot expert systems are taking over many jobs in industries that are dangerous for or beyond human ability. Some of the applications divided by domains are as follows. Aviation. Here we have shown few key concepts of AI. Ant colony optimization, which we are going to analyze further. And others are artificial immune system, developmental robotics, expert system, genetic algorithm, hybrid logic, intelligent agent, knowledge-based engineering, machine learning, multi-agent system, and soft computing. Ants. Individual ants are simple insects with limited memory and capable of performing simple actions. However, an ant colony expresses a complex collective behavior providing intelligent solutions to problems such as carrying large items, forming bridges, and finding the shortest routes from the nest to a food source. A single ant has no global knowledge about the task it is performing. The ant's actions are based on local decisions and usually unpredictable. The intelligent behavior naturally emerges as a consequence of the self-organization and indirect communication between the ants. This is what is usually called emergent behavior or emergent intelligence. There are many other examples of emergent behavior in nature, such as colonies of bacteria, bees, and so on. There are even theories that explain the human conscious as an emerging behavior from the interactions and self-organization of the simply individual neurons, but this we can discuss in another opportunity. How do ants and social insects coordinate their activities? Self-organization. Individual insects living in colonies such as ants, bees, do their own specific task, and yet the colony is well organized and it does not require any kind of supervision. This is called self-organization. The fascinating behavior of ants has been inspiring researchers to create new approaches based on some of the abilities of the ants colonies. Some of the existing applications include the traveling salesman problem, graph coloring, logistic, and lot more. In order to solve this problem, some characteristic of ants colonies will be particularly useful. Their ability to find the shortest route between the nest and a food source, which will be used to find and optimize a path in the graph. Also, they are capable of adapting to changes in the environment. For example, finding a new shortest path once the old one is no longer feasible due to a new obstacle. The simplicity of each individual ant, which will make it easy for us to model the ant colony as a multi-agent system. The original idea comes from observing the exploitation of food resources among ants, in which ants' individually limited cognitive abilities have collectively been able to find the shortest path between a food source and the nest. The first ant finds the food source F via any way A, then returns to the next N, leaving behind a trail pheromone B. This figure shows how ants indiscriminately follow 4 possible ways, but the strengthening of the runway makes it more attractive as the shortest route. Finally, ants take the shortest route. Long portions of other ways lose their trail pheromones. A model explaining this behavior is as follows. An ant runs more or less at random around the colony. If it discovered a food source, it returns more or less directly to the nest, leaving in its path a trail of pheromone. These pheromones are attractive. Nearby ants will be inclined to follow, more or less directly, the track. Returning to the colony, these ants will strengthen the route. If 2 routes are possible to reach the same food source, the shorter one will be traveled by more ants than the long route will. The short route will be increasingly enhanced and therefore become more attractive. The long route will eventually disappear. Pheromones are volatile. Eventually, all the ants have determined and therefore chosen the shortest route. Figure 2 describes the ants capable of adapting to changes in the environment. For example, finding a new shortest path once the old one is no longer feasible due to a new obstacle. In Figure A, real ants follow a path between nest and food source. In Figure B, an obstacle appears on the path. Ants choose whether to turn left or right with equal probability. This figure C shows how pheromone is deposited more quickly on the shorter path. Finally, in Figure D, all ants have chosen the shorter path. When ants are released into the box, they immediately start their random walk inspired by Brownian movement. Ants follow random length headed to some initial random direction. When they reach the end of the segment, a new direction is chosen. Each ant has two status, foraging and going home. If an ant is going home, it does just that until it gets home, whereupon it turns around and starts foraging again. As an ant home, it drops pheromone which spreads slightly and dissipates over time. If an ant it tests in front for pheromone and turns towards the direction where there is greater concentration of pheromone, the ants also randomly turn slightly so that they will explore new area. When there is no pheromone to be found, if an ant collides with some food, it picks it up, start going home. Applications of ant colonization. Traveling salesperson problem, which is we mainly focused, and others are knapsack problem, job shop scheduling problem, vehicle routing problem, assignment problem, set problem. Traveling salesperson problem. The traveling salesman problem is one of the most intensively studied problems in computational mathematics. Given a set of entities, the traveling salesman problem requires a salesman to find the shortest route between the given cities and return to the starting city, while keeping in mind that each city can be visited only once. The traveling salesman problem, or TSP for short, is to find the cheapest way of visiting all of the cities and returning to a starting point. In the standard version we study, the travel costs are symmetric in the sense that traveling from city X to city Y just costs as much as traveling from Y to X. The simplicity of the statement of the problem is deceptive. The TSP is one of the most intensely studied problems in the computational mathematics, and yet no effective solution method is known for the general case. Although the complexity of the TSP is still unknown, for over 50 years its study has led the way to improve solution methods in many areas of mathematical optimization. TSP applications. Lot of practical applications. Routing such as in trucking, delivery, UAVs. Manufacturing routing such as movement of parts along manufacturing flow or the amount of solder on circuit board. Network design such as determining the amount of cabling required. So, what does this all mean? Computer can work out the TSP but increase the amount of units involved and the computer starts to struggle. Devising algorithms for finding exact solutions will only work reasonably fast for relatively small problem sizes. So, when you increase the set of instructions, a computer will take longer to process the data. We hope you understand more about the traveling salesman problem. We thank you for viewing this presentation and hope you have learned a little bit more about AI and how it is related to our selected problem.
The traveling salesman problem. When we considering the traveling salesman problem, we can have a look at that problem in two different aspects. Informally, the problem of finding the shortest tour through a set of